So now let's talk about a completely different example, this time from physiology. We talked about hormone control and the idea that the target organs, the gonads, the thyroid, are under negative feedback control from the brain. And we would like to understand this physiologically and mathematically. So hormones, as you are learning, are chemicals that are secreted by various organs, the thyroid, the pancreas, the adrenal cortex, and the gonads. And I'm going to focus on gonadal hormones in this example because that was the first example that was really heavily studied. So the gonads put out hormones. I mean, they have names. In males, it's testosterone. In females, it's estradiol and progesterone are the major gonadal hormones. But I'm going to ignore all that detail. And I'm just going to say the gonads put out a hormone, and the hormone is called G. That we know. Now, what causes the gonads to release G? Well, research demonstrated that there's a gland in the head, although not in the brain. It's on this side of the blood-brain barrier. So it's in the head, but not in the brain, called the pituitary. And the pituitary releases a hormone. And again, these have fancy names: luteinizing hormone, releasing hormone, follicle stimulating hormone. I'm not interested in the details. I'm going to symbolize all of that with a single hormone coming from the pituitary, exciting the gonad and causing the gonad to release G, and I'm going to call that pituitary hormone P. And I'm putting in a plus sign there to indicate that the pituitary chemical P positively causes release of G. The more P, the more G. Okay, that's good. What causes the pituitary to release P? That research wasn't done until the 70s. And it turns out that there's a small, very important gland in the brain called the hypothalamus. And the hypothalamus secretes releasing factors that cause the pituitary to release their hormones, which cause the gonads to release their hormones. So again, there are fancy names for the hypothalamic factors. I'm going to forget about that. I just want to call all of them by a single name. I'm going to call them H. And so H is the hypothalamic hormone. And once again, the hypothalamic hormone causes the pituitary hormone output to increase, which causes the gonadal hormone output to increase. So, okay, we're tracing this backward. And you're now thinking, well, where does this end? And the answer is, it ends right here. It ends with negative feedback of the gonadal hormone onto the hypothalamus. In other words, this is a negative feedback loop. And you might think, well, does this negative feedback loop produce homeostasis, as it was said to? This is the negative feedback of the brain on the gonads. And so in order to decide that, what does this model predict? Well, this picture doesn't predict anything. And as a matter of fact, unfortunately, biology is filled with these boxes and arrows or circles and arrows diagrams of this increases this and this decreases that. These diagrams are nice, but they don't make predictions. You can't make a prediction based upon this diagram. You have to make a differential equation. So let's do it. So we have three factors here, H, P, and G. We're going to make a three-variable differential equation, H prime, P prime, G prime. So first, let's start with the easy terms. Let's look at P, for example. What makes P go up? Answer, H. What makes P go down? Answer, degradation of P, a certain constant quantity, a constant fraction of P is metabolized, is peed away, is degraded by the system. And so we're going to have a positive term, which is H, and we're going to have a negative term, which is K1P, where K1 is the degradation rate of the hormone P due to the kidney, various other processes. So that's easy. If we go to the gonad itself, that's also easy. What makes G go up? Answer, P. P makes G go up. What makes G go down? Answer, secretion, degradation, just first order wastage of G, and that's at a rate K2. And so our G prime equation is P minus K2G. Now comes the hard part, which is we have to figure out how to write that hypothalamus term. So I'm just going to write it in English for a second. The hypothalamus term is going to have to incorporate the negative feedback. It's going to be some function of G. G has to go into H, into the H prime equation. And that's what that negative feedback term has to do. And then we're also going to decide that the hypothalamic hormone is also degraded at a rate K3. And now for the rest of this discussion and for all of our simulations, we're just going to assume that K1, K2, and K3 are all 0.2 to get some degradation. And that's K1, K2, and K3. So now we got to think about this negative feedback term. How are we going to make a negative feedback term? Well, there's several kinds of negative feedback. There's negative, for example, there's negative feedback that actually subtracts from the quantity in question. For example, if you have a thermostat and you have an air conditioner, then if the room gets warm, the air conditioner kicks in and actually lowers the temperature. But the hormone endocrine system cannot suck up hormones. It can't take them away. It can only reduce the production. So it's like you only had a heater. Your thermostat can't make it colder, but it can turn down the heater. And that's the negative feedback that is relevant here. The negative feedback cannot create a negative term. It has to turn down the hypothalamic output because the hypothalamus cannot reuptake the hormone, can't suck up the hormone. So a very simple function that could reflect how the negative feedback term would work. Where is this? A very simple function that would reflect how the negative feedback works is a downgoing sigmoid. So what this says is that for low values of G, the negative feedback term is large, but that as G increases, the negative feedback term in H prime gets smaller and smaller and smaller. So G turns off H. And so we want a downgoing sigmoid, and we know the equation for a downgoing sigmoid. Downgoing sigmoid in G would have the expression 1 over 1 plus G to the n. And remember, with negatives, downgoing sigmoids, and also upgoing sigmoids, the n modulates the steepness of the negative feedback. So the black is n equals 3. That's mild negative feedback. The red, which is n equals 5, is steeper, more sensitive and steeper negative feedback. And the blue, which is n equals 9, is even steeper still. So we can modulate the steepness of the negative feedback. That is to say, we can modulate the sensitivity of the hypothalamus to circulating levels of G. And we can do an experiment to see what happens when G is large and when G is small, but also we can experiment what happens as the sensitivity of the hypothalamus changes. For example, from the black curve to the blue curve. So let's do some simulations. Let's first try our new differential equation with an n of 3. What we see is stable equilibrium behavior. No matter where we started, there was an initial excursion, but it quickly went to a stable equilibrium. If you perturb off that, it's going to go back to that stable equilibrium. This system does indeed have a stable equilibrium point. But if you now make that system, make the hypothalamus very sensitive to circulating gonadal hormones, you steepen the slope of that function, let's say n equals 9, and you do the simulation, and you get a very different result. The 3 hormones oscillate, and they oscillate in definite phase relations. Notice that H leads P and P leads G. Here's H leads P and P leads G, which is exactly what you'd expect from the causal relations in the feedback loop. So this has produced an oscillation. If you plot it in the 3-dimensional state space, you see that it zooms to a loop which is sitting sort of in general position in 3 space. And then you can also do the experiment. Now here I'm going to show you a 2-dimensional projection of this. You can do the experiment of starting at lots of different initial conditions. If you start at this initial condition, you go quickly off the screen, but then notice the blue trajectory comes right back in and zooms around the loop. The orange trajectory, again, zooms back in and right around the loop. The green trajectory, which started out outside, also zooms into that loop. And so we have here a second example of a stable limit cycle. That is to say, a limit cycle attractor. Now, I want to talk a little bit about this mechanism, the mechanism of oscillation in the HPG model. Well, you saw what we did. We just changed the n from n equals 3 to n equals 9. And by changing that, that is by steepening the slope of that curve, we went into stable oscillation. There's a nice kind of homespun example that illustrates this sensitivity to feedback as a cause of oscillation. I want you to imagine a parent teaching a kid to drive. So the kid is trying to maintain pretty much equilibrium down the center of the lane, and the parent is supplying negative feedback, like, you're drifting a little too far to the left, correct right. You're drifting a little too far to the right, correct left. And with a nice, mellow parent, that is going to produce stable equilibrium behavior down the center line of the lane. But now imagine a hysterical parent, shown here. This parent's feedback function is very steep. And so their control commands are going to be of the form, you're drifting too far to the right, correct left. You're drifting too far to the left, correct right. What is going to happen to the driver? And the answer is the driver is going to start oscillating around the center point of the lane, but will never get to the center point of the lane because she's always overcorrecting and then overcorrecting the overcorrection because the parent is giving very harsh commands. The parent has a very steep feedback function and issues very strong commands at slight deviations. So the moral of the story, and this is a very important take-home message, the moral of the story is a feedback system that might have maintained an equilibrium at low slope, at insensitive feedback. As that feedback becomes more sensitive, that system will go into oscillation. And it's interesting in that respect to note that in the endocrine system, where hormone cycling begins in earnest at puberty, we want to ask, well, what is the cause of this onset of cycling behavior in females and in males, although that's not as widely known? What is the cause of the onset of the cycling behavior? We can now look for an increase in the sensitivity of the feedback loop, and we find it in the form that there's a real upregulation of hypothalamic receptors for the gonadal hormone occurring right around puberty. In other words, the system gets more sensitive and the feedback becomes harsher and the system goes into stable oscillations.